Hello everyone, welcome to this lesson. So in this lesson we're going to go through our first method to find roots of equations, and that's going to be the bisection method. And the bisection method is a very simple method. It's part of a umbrella of techniques called the bracketing methods, where they actually bracket the root as they actually go about finding the root. So the bracketing method can be summarized in this equation here, where we find the root by taking two bracketing values, the upper limit and the lower limit, and we get an average of them, and we keep applying this in multiple applications as we get to the accuracy that we are after. So how does this work? So actually, let's take the function that I introduced in the previous lesson, which is x squared minus x minus 2, and you can find that it has two roots, one at -1 and one at 2. So let's actually go about finding the root at 2. So the first thing that you would do is you would find two values that would bracket the root. And here I'm gonna use 1 and 2.5. So they bracket the root of 2 is actually between those two values. And what I'm gonna do is I'm going to apply this equation here and to get my first estimate of the root. So basically it's the average of these two values, which I have 1.75. Now, we know what the root is, which is 2. So let's actually get the true error. So true error in this case is going to be 12.5%. So given that I have my first estimate of the root, the second thing that we're going to be doing as part of this technique is identify where is the root in these two sections, because by creating an average here, you have a section here between the lower limit and the root, and you have another section between the root and the upper limit. So I need to define which of these two intervals has the root. And the one thing that we're going to be doing this is by identifying how the function is changing within the interval. What do I mean by that? If you look at the function value at the lower limit, you're going to find that it has a negative value. And if you look at the function value at the root, it has a negative value. It has the one at the upper limit, it has a positive value. So the interval in which the function has a change in sign, in other words, the x-intercept, this is going to be where my root is. So the change in sign in the function is going to be the piece of information that we're going to be using to find the interval, especially when we're going to be writing the code, the interval where the root is at. So we know that the root here is between the interval of 1.75 and 2.5. So in other words, the root here becomes the lower limit, as you can see in the second application here. So the second application here, the lower limit is 1.75, the upper limit is still 2.5, and if we apply this equation, which is merely an average of the two values, we get 2.125 as our new estimate for what is the root here. And if I apply the error equation, and in this case I'm going to take the absolute value, we have 6.25% error, and you can see it's an actual improvement on the first application that we did here. Much like what we did here, we're going to find which interval houses the root, and again, the thing that we're looking for is a change in sign for the function, and you're going to find that there's a change in sign between the lower limit and the root of 1.75 and 2.125. And then this becomes my new interval. As you can see in the third application here, we're going to apply this equation again, take an average of these two values, 1.75 and 2.125, and we're going to get 1.9375. Now, if you look at what is the true value or the true error of this is 3.125%, which is, again, you can see an improvement on the second application. And you keep doing this. You actually keep identifying which interval has the root, you half it again, and you keep doing this as you get closer and closer and closer to the root, depending on your error tolerance. So depending whether your error tolerance is 0.1%, 0.01%, and we're going to be examining this more specifically in the Python code, because you can see here 3 application of the bisection method got us to 3.125%. Then we're going to be assessing how many applications, for instance, will get us to 1% or 0.1% or 0.01%. Now, in this lesson, you can see the bisection method is actually a very, very simple method. It's just the averaging of an upper and lower limits. And the second step is you identify where the root is in the bisection. This is where the name is coming from, the bisection that you've created, and you keep halving and identifying the new interval, half identifying the new interval, and so on until you converge to the error criteria that you're after. So you can see it's a very, very simple method. Now in the next lesson, we're going to be developing the Python code for this, and we're going to be examining it for different error criteria and identifying how many bisections do we need to apply to converge to the answer that we are interested in. Well, that's it for this lesson, and I will see you in the next lesson.